to the lecture series of switching theory and logic design. Our next unit is sequential circuits part 2. So this is our next topic. So let us come into here. We will discuss the concepts in this unit are, first one, finite state machine. For understanding the finite state machine, we have to know the basic definitions of state diagrams, state tables, and we have to see the reduction of state tables. For implementing finite state machine, we have to know these three parameters. Next, analysis of clocked sequential circuits, Mealy to Moore conversion, and vice versa. This is the next topic. And realization of sequence generator, design of clocked sequential circuit to detect the given sequence with overlapping and without overlapping. These are the topics we are going to discuss in this unit. Next, finite state machine. So, the finite state machine itself, it is saying that it has some finite number of states and we have to implement that type of machine. That is basic information about the finite state machine. Now, coming to this is a generalized block diagram of a finite state machine or finite state model. The empty box of this one, which is representing some of the combinational circuit behavior or some of the sequential circuits behavior. That means in this block we are giving some of the combinational circuits and some of the sequential circuits. The combinational circuits operating with the inputs and it produces the outputs, and some of the sequential circuits which are operating with the clock also and they have some of the inputs and previous state of the outputs we are taking from here. So the output of this combinational circuits we are connecting to the sum of the memory elements. These are we are representing with y1 to yk, and these outputs are we are connecting to the input as a combinational logic circuit, and these combinational circuits process the outputs. So this is the finite state machine generalized model. This is in this block we are consisting of some of the combinational and sequential circuits, and these are controlled by the inputs and clock signals. The output of this circuit we are storing in the some of the memory elements. So these are the previous state of the outputs for processing the present state of the outputs. Otherwise, for processing the next state of the outputs, we are taking the inputs of this present state of the outputs. So this is the generalized block model for finite state machine model. Next, coming to that, here the mathematical representation of synchronous sequential machine. So now we will see how to represent some of the finite state machines are the basic models with the mathematical representation. Actually, in the finite state machines, we have two types of machines. The first one is Mealy model and second one is Moore model. The relationship between the present state is we are representing S of t, and the present input we are representing with x of t, and the next state we are representing s of t plus 1, where s of t is the output of the system, but where s of t is the present state output and s of t plus 1 is the next state outputs, and x of t is the input. Now, the s of t plus 1, that is the next state output we are defining with the function of s of t comma x of t. Here we can write some function f of s of t comma x of t. The next state output is depends upon the present state and input. Now, see here, the values of the output z of t can be given as, that is the output, the next state output we are defining with z of t. The z of t is equal to some function g of s comma s of t comma x of t. That is the output of the system is depends upon the present state and input. This is for Mealy type machine, and z of t is equal to g of s of t. That is equal to, this is Moore type machine. This is Moore type machine. Now here we will see the models of Mealy circuit model and Moore circuit model. So see here the Mealy circuit model. Here this is the output and these are the inputs. So why I said the first outputs? We have seen the definition of the Mealy model just now. The output of the Mealy model is depends upon the present state. So the present state is nothing but as output of the system. The S of t here we have, and coming to here, these are the inputs. So the direct inputs I have given here. The direct inputs I have given here for the final output decoder, and these are the next state decoders and some of the memory elements which are stores the previous state values. So these are the S of t and this is X of t. So the output, that is Z of t of this form of this Mealy model circuit diagram is depends upon the X of t and S of t. So here you have to take output as Z of t. This is Z of t, right? Where the Z of t is equal to some function of S of t comma X of t. So this is a Mealy type model circuit mathematical representation for the output. Okay, so this is the generalized block diagram. In this block diagram, we have the finalized output decoder. For this finalized output decoder, we are giving one side inputs and another side we are giving memory elements, where these memory elements are the next state decoder. So actually the next state decoder outputs are nothing but as we are collecting from the output decoder. That is the previous state or the present state of the outputs we are taking here, and we are giving to the next state decoding purpose. So these are we are storing at the memory elements, and these memory elements giving the this present state outputs to the output decoder, and finally we can get the next state outputs. That is Z of t is equal to some function of S of t comma X of t. Now let us see. This is an example of Mealy model without any output decoder. Here, the outputs of the system is depends upon the completely memory elements. Generally, the memory elements collects the output of the system and it will stores the present state of the outputs and it will generate the next state of the outputs. That is, Z of t is equal to S of t. This is for Mealy model. The output Z of t is equal to some function of G of S of t. So this is the Mealy type machine, Mealy type model. So we have the Mealy type model with some output decoder also. Here we have the next state decoder and memory element. The inputs we are giving to the next state decoder, and this next state decoder will give the next state behaviors by using the memory elements. From this memory elements we are taking the outputs. So this is the Mealy type model. Right. So here the memory elements, whatever the outputs we are taking from the output side, these outputs we are taking the feedback to the next state decoder. Now these outputs we are giving to the next state decoder, and here we have some of the inputs also. So these inputs and present state of the outputs combined we are giving to the next state decoder, and the memory elements processing these informations, and finally we are collecting the outputs. So see here, the outputs completely depends upon the memory elements only. Okay, there is no necessity of writing the inputs. The inputs are not mandatory in this Mealy type model. The inputs are not mandatory. Okay, the previous state is mandatory for getting the output Z of t. So this is about Mealy type model. The Mealy type model, here we are representing with an output decoder. Here we have output decoder, and this output decoder which are collecting the outputs of the memory elements, and the finalized function we are implementing with this Mealy type model. Okay, so after getting the complete output from the memory elements, these memory elements we are getting some output, the next state output. The next state output we can use for implementing our required function by using output decoder. So this is a Mealy type model, Mealy type machine with the required outputs. Okay, right. Next, all of you note it down. Next, coming to that, we have to see some of the basic definition for better understanding the finite state machine. For better understanding the FSMs, we have to see state diagram. What is the mean by state diagram? What is meant by state table? These are the definitions we have to see. So coming to here I am drawing a state diagram where the state diagram is consisting of 5 states, where the states are nothing but as some of the outputs of our combinational circuit. These are the 5 different output states. For example, take this one 0 0. So after 0 0 we will get generally 0 1. That is I am considering here. After 0 1 I will get 1 0. After 1 0 I will get 1 1. Right? These outputs combinations I am representing here with some A B C D E terms. Okay, right. So present output is 0 0. Then what is the next state output? If A is the present state, then what is the next state output? The next state output may be B, or next state output may be D, next state output may be C. Generally, we have the 2-bit possible combinations 0 0 0 1 1 0 1 1. But when you are doing some of the experiment or doing some of the operations, so after 0 0, you maybe get 0 1 or 1 0 or 1 1. You can get any type of output. So see here, I am writing. So A is the present state and D is the next state. Okay, here I have represented some 1 by 1 configuration. So here the first one is representing the input and the second one is representing the output. Here I am representing the input and output behaviors with 1 by 1, where the first one is representing input and the second one is representing the output. Now, so when input is equal to 1, the present state is A, next state is D. Okay, there may be a chance of getting input 0 also. If input is 1, the A is the present state, D is the next state. If input is 0, A is the present state, B is the next state. Okay, for each state it has 2 inputs, either 0 or 1. If it is 0, it is shifting to B. If it is 1, it is shifting to D. Okay, like that. Next, see the B state. From B state, if input is 1, it is shifting to A. If input is 0, it is shifting from B to C. Next, here C is there. If the present input is 1, then it is shifting to the A. If the input is equal to 0, from C to we are shifting to the D. So this is the, from C to, if input is 0, 1, these are the transition. So from C to D, we are going the state D. That is also called state transition. Right. Now, present state is D. Next state is D. Now the state transition is there from D to E. Okay. State transition is there from D to E whenever the input X is equal to 0. And next, coming to that, present state is E. Here we have the present state is E, and if the input is equal to 0, then the next state is E. Okay, here we have a logic. If the present state is E, next state is also E. Okay, so there may be a chance of getting the same state again. That is, previous output follows as the present output. This combination we have seen in the flip-flops and latches. The same output maybe we will get. So this is an example of the state diagram. This is an example of the state diagram. From the state diagram, now you have to draw the state table. So here total we have A, B, C, D, E. These are the 5 states. Now I am writing present state. The present state. The present states, here we have totally A, B, C, D, E. These are the present states. Then next, coming to the next state. Next state. Here we have input X is equal to 0, X is equal to 1. Here I am taking some X is equal to 0, X is equal to 1. 2 conditions I have taken here. Now, see here. If A is the present state, then what is the next state? Here from A to we have D state, we are going to the B state. 2 type of state transitions we can see. When X is equal to 1, the next state is D. When X is equal to 1, the next state is D. When X is equal to 0, that is input is equal to 0, the next state is B. So this is B. Okay, next. Coming to that, present state is B, next state is C if X is equal to 0. That is, here we have to write down C. Next, if the present state is B, next state is A when X is equal to 1. That is, input is equal to 1. So this is A. So this is the next state decoding. This is the present states, these are the next states. Next, present state is Z. Next state is J when X is equal to 1. This is A. Next, present state is C. Next state is D when X is equal to 0. That is input is equal to 0. That is D. Next, present state is D. Next state is E when X is equal to 0. So D, E. Next, here when it is D, we have to check the present state is D. There is no input X is equal to 1. We are not defined. So here there is no state for the D when X is equal to 1. We have not defined the next state. We have left that. Next, present state is E and next state is also E if X is equal to 0. So this is E. And for 1 we have not defined. For 1 we have not defined. So this is about present states and next states. And see here, output is also there. Present state A, next state is D, and output is equal to 1. So next state B is B comma 1 you have to write. So B comma 1, it's not B comma 1. Right? D comma 1. Why? Because from A to we are shifting D and input is 1, output is 1. Input is 1, output is 1. Next, A to B we are shifting. When input is equal to 0, output is also 0. We have to write here B comma 0. Next, from B to C. Here, when it is shifting to A, the output is 1. When it is shifting to 1, the output is 0. From C to here, when you are shifting to A, the output is 0. When you are shifting to D, both the outputs are zeros. Okay, next. When you are shifting from D to E, the output is 0. Right. When you are shifting, so see here we have a logic. We forget that. From E to we are going to again E. Whenever the X is equal to 0 and X is equal to 1. For both combinations, the next state is E. I forgot that. Now coming to the output, for both states, output is 0. For both states, output is 0. So this is the state diagram. And this is the state table. Okay, right. Now see here the basic definitions here. First state diagram. So see here A, B, C, D, E. The same example I have written here. Now I am taking the definition of successor. So for coming to the state diagram definition, a state diagram is a diagram which is representing all the possible states of a machine, and it will represent the flow of the present state to next state, or it gives the state transition, and it will give the behavior of the state transition whenever the inputs of the but that particular state is equal to 0 and 1. For both combination, it will represent the next state behavior. Now coming to the definition of successor. So here in the state diagram, you have to know what is meant by successor. Here I have written something. See here, A is the present state, right? And inputs is 1, then next state is T. A is the present state. If input is equal to 1, then next state is D. Okay, then D is the one successor of A. So D is the one successor of A. D is the one successor of A. That means if A is equal to present state, if input is 1, then the next state is the D. Now D is the one successor of A. In the same way, see here, A is the one successor of B and C. A is the one successor of B and C. That is, here A is the next state and present states are B and C. Here, whenever B is equal to B, input is equal to 1 at the B and C states, the output is A. Now, A is the one successor of B and C. So see here, D is the one successor of A. A is the one successor of B and C. Okay, now see here, D is the one successor of B, D is the one successor of C. That is, D is the one successor of B and C. So see here, D is the one successor of B and C. This is the last statement. So this is the definition of successor. The successor is representing the output and the present state and the next state behavior with the input value. If it is one successor, it will goes to the whatever the one state, the one present state and one next state. If 0 successor is there, then it will guide the path of the 0, what is the present state and next state, and the state transition with 0 transmission or 1 transmission. These are the behavior of the successors. Next, coming to here, one more definition. Terminal state. Terminal is the last state, terminated state. You can call this one as terminated state. A terminate state. A state is the terminal state when there are no outgoing arcs. So I am saying that these are the arcs, right? So if there is no outgoing arcs which start from it and terminates in other states. So see here the E state, see here, it is starting from here and it is ending with here only. There is no chance of getting another state from E. So E is the end point. There is no other state from E. So you can call E is the termina, that is the final state or terminated to other state. There is no other state here. So you can call E is the terminal state. That is the final state. So example is E state from our diagram. Okay.